ever feel like we're just scratching the surface of what's really out there?
Mm-hmm.
I mean, the universe is vast, obviously,
Oh, yeah.
full of mysteries,
Yeah.
and honestly, a bit intimidating.
Yeah.
But today we're taking you on a deep dive into a realm where some of those mysteries might actually be unlocked.
Okay.
Theoretical physics.
Wow.
Don't worry, we're starting with a fascinating paper on killing superalgebras in 2 dimensions by Andrew D.K. Beckett.
Yeah.
And while the title might sound like something out of a science fiction novel, it actually holds some real-world implications for our understanding of the universe. Our mission today, to equip you with a solid understanding of what these mathematical constructs are, why they're important to theoretical physics, and how just a few, tiny tweaks within these mathematical frameworks could point to the existence of entirely different universes.
So we're essentially talking about the mathematics behind universe building here.
Exactly.
Yeah.
Now, anyone who follows theoretical physics has probably heard whispers of something called supersymmetry.
Right.
And I'm not talking about some superhero team-up movie,
Yeah.
although that does sound pretty entertaining.
Right.
But
supersymmetry takes our current understanding of particles and adds a fascinating twist.
Okay.
Essentially, it proposes that for every known particle,
yeah.
there's a super partner particle.
So like a buddy.
Yeah, like a partner in the universe, if you will. It's a concept that could revolutionize our understanding of forces and particles.
And leads to some seriously cool, though theoretical, outcomes like supergravity theories.
Exactly, and that's where these killing superalgebras come in.
Okay.
They provide the tools, the mathematical frameworks for exploring symmetry within those supergravity theories.
So we're trying to unlock the secrets of the universe.
Yes.
And these algebras are the keys.
They are.
Now, Beckett's paper, published just last month, uses a simplified 2-dimensional model to make the math a bit more digestible.
Right. Think of it as a necessary stepping stone.
Okay.
Before we can comprehend the symphony of a full-blown orchestra, sometimes it helps to isolate the individual instruments.
Right. So we're breaking down the symphony of the universe into, like, individual notes.
Get that.
Okay, so with that in mind, let's unpack one of the key ingredients in this paper. Miters.
Okay.
They sound like something straight out of a physics textbook.
They are, but they're also much more than that.
Okay.
Imagine an arrow existing not in our physical space, but in an abstract mathematical space.
All right.
That's what we're dealing with here.
Okay.
They have a direction, like an arrow.
Yeah.
But when you rotate them in this space,
Mm-hmm.
they don't behave the way you'd expect.
Not your average arrow, then.
Not at all.
Okay.
A regular arrow makes a full rotation at 360 degrees, right?
Right.
Spinors, on the other hand, require a 720-degree rotation to return to their original state.
Wow.
It's a mind-bending concept, but crucial to understanding their behavior.
So we're already venturing into some pretty strange territory here.
We are.
But it gets even more interesting because Beckett's paper then introduces something called squaring maps, which sounds complicated.
Perhaps a bit, but think of it this way. A squaring map provides a way to take two of those spinors, combine them in a specific way.
Okay.
And what emerges
Yeah.
is something that behaves like...
Gravity. Hold on, we're building gravity out of mathematical arrows now.
In a sense, yes.
Okay.
And what makes it even more fascinating is that there are different types of these squaring maps characterized by a value called sigma b.
Right.
It can be either 1 or matic 1.
Seems a minor detail.
It's anything but.
Okay.
This tiny difference in sign creates two distinct categories of squaring maps. And as Beckett demonstrates, each category results in fundamentally different universes when we start building these algebras.
So just by switching a plus sign to a minus sign,
exactly,
we've essentially shifted to an entirely new set of universal building blocks.
Precisely.
Wow.
It's like having all the ingredients for a cake,
but
swapping out sugar for salt.
Oh.
Same starting point, dramatically different outcome.
I'm starting to see how even the smallest details matter on this level.
They do.
But how do we even begin to classify these different universes, these different families of killing superalgebras?
That's where things get really interesting.
Okay.
Beckett uses a technique called Spencer cohomology.
All right.
You can think of it like analyzing fingerprints.
Okay.
Each algebra possesses a unique fingerprint revealed through this method.
So are we dusting for mathematical fingerprints now?
In a way, yes.
Okay.
And by carefully examining these fingerprints, Beckett's paper identifies two distinct families of killing superalgebras.
Oh, okay.
Each tied to one of those two squaring maps we talked about.
So we have two sets of building blocks, two distinct families of algebras. Are we talking about two potential universes here?
That's what's so intriguing about this work.
Okay.
It opens up the possibility that our concept of the universe might be far too limited.
Yeah.
But to explore that further,
yeah,
we need to delve deeper into how these algebras are used to construct these mathematical universes.
Okay.
And that's where things get even more interesting. Picking up where we left off, you'll recall we've been dissecting these two families of killing superalgebras. Each like a distinct set of blueprints for a universe.
Are two recipes for cosmic cake, as it were?
Precisely. But blueprints, recipes, they only get you so far.
Right.
To breathe life into these mathematical constructs.
Yeah.
Beckett introduces the concept of admissible connections. Think of these as the laws of physics governing those universes.
So if the algebras define the ingredients of a universe,
yes,
the admissible connections determine how those ingredients interact, how everything unfolds.
An excellent analogy. And what's truly fascinating
is
that Beckett demonstrates how the choice of squaring map, that seemingly insignificant plus or minus sign, dictates which set of admissible connections, which set of physical laws emerges.
So we're talking about tweaking a single sign in an equation, and suddenly gravity behaves differently. Light bends in new ways. Entire universes, each with its own unique set of rules, springing into existence.
It underscores the incredible sensitivity of these systems to even the slightest mathematical alterations.
Yeah.
It's like navigating a multiverse of possibilities by simply adjusting a dial.
A multiverse dial. Okay, theoretical physics just got a whole lot more science fiction-y in the best way possible.
Yeah.
But there's one more piece of the puzzle we need to address. Killing spinors. What exactly are these, and how do they fit into these mathematical universes?
Remember those spinors, those arrows in abstract mathematical space?
Right, yeah.
Killing spinors are special solutions within the framework of those admissible connections.
Special in what way?
Imagine you're studying the flow of water in a river. There might be certain points where the water appears to stand still.
Right.
Caught in a delicate balance of forces. Those are like our killing spinors. They represent points of stability, of invariance within the dynamic system governed by the admissible connections.
So they're like those perfectly balanced rocks you sometimes see seemingly defying gravity.
Precisely. They represent a kind of equilibrium, a harmony within the system.
Okay, so we've got these mathematical universes, each defined by its own set of rules, and within those universes we have these points of equilibrium represented by killing spinors.
Yes.
But how do we go from abstract mathematics to something resembling our physical reality, something we can actually visualize?
That's where the true beauty of Beckett's work shines through.
Okay.
He takes these abstract constructs and gives them geometric meaning. He bridges the gap between the theoretical and the tangible.
Okay.
And here's where things get really mind-bending.
I'm strapped in and ready for the ride.
Good, because Beckett demonstrates that those abstract universes, at least in their simplified two-dimensional forms, correspond to actual geometric spaces.
Okay, now you've officially piqued my curiosity.
Okay.
We're talking about shapes, dimensions. Give me something concrete to grasp onto here.
Imagine for a moment a saddle.
Okay.
Now, extend that saddle shape infinitely in all directions.
Okay.
That's what we call hyperbolic space.
Okay.
It's one of the geometric realizations that emerge from these killing superalgebras.
So instead of a flat grid, we're talking about a universe curved like an infinite saddle.
In one scenario, yes.
Okay.
And it's not just some mathematical curiosity. Hyperbolic space has profound implications for our understanding of geometry, gravity, and potentially even the shape of the universe itself.
This is incredible.
Yeah.
But what about the other scenario, the other set of admissible connections? What kind of geometric space does that lead to?
This is where it gets even more interesting, if you can believe it.
Okay.
Depending on specific parameters, this second scenario can give rise to either de Sitter space or anti-de Sitter space.
Okay.
Both of which are incredibly important in cosmology.
Cosmology, the study of the universe as a whole. We're finally going macro here.
Yes.
Tell me more about these spaces. What makes them so special?
Well, imagine a universe where expansion is accelerating, where the very fabric of space-time is stretching at an ever-increasing rate.
Okay.
That's de Sitter space. On the other hand, anti-de Sitter space describes a universe with a kind of inward-pulling gravity, leading to a potential collapse.
So we're talking about two radically different fates for the universe.
Yes.
And it all hinges on those subtle mathematical choices we made earlier.
It highlights the profound implications of these theoretical frameworks.
Yeah.
By simply adjusting a few parameters, by exploring different branches of these mathematical equations, we're essentially peering into a multitude of potential universes.
It's both exhilarating and a little terrifying, to be honest.
Sure.
But before we get lost in the multiverse, let's bring it back to Beckett's paper.
Okay.
What's the big takeaway here? What does it all mean for our understanding of the universe?
So we've journeyed deep into the mathematical wilderness with these killing superalgebras, explored different universes built from them,
right?
Even glimpsed their geometric forms. Where's all this leave us?
Well, what Beckett has accomplished is remarkable.
Yeah.
He's shown us that by simply, shifting a sign in an equation,
right,
by exploring these different families of algebras,
yeah,
we unlock a whole range of possibilities for how the universe might be structured.
It's like those old choose your own adventure books.
Right.
But instead of deciding between like a spooky forest and a hidden cave,
yeah,
we're choosing between a universe shaped like an infinite saddle,
yeah,
or one expanding at an accelerating rate.
Exactly. And remember,
yeah,
this paper focused on 2 dimensions for the sake of simplicity.
Right.
Imagine the possibilities when we apply these tools to our own 4-dimensional universe.
Okay.
Or even, higher dimensions. My brain's already starting to melt a bit just thinking about it.
Sure.
But in a good way, I promise.
Of course.
So what you're saying is this paper isn't just some abstract mathematical exercise.
No, not at all.
It has real implications for how we understand the cosmos.
Absolutely.
Okay.
It suggests a universe far more complex,
yeah,
far stranger,
okay,
and far more open to possibilities than we might have previously imagined.
Wow.
It challenges us to rethink our assumptions about the very fabric of reality.
And that's what makes theoretical physics so captivating.
It is.
It's not just about equations on a chalkboard.
Right.
It's about pushing the boundaries of human understanding.
Yes.
About grappling with the biggest questions we can possibly ask.
Absolutely. And who knows?
Yeah.
Maybe someday, through explorations like Beckett's, we'll find the answers,
right,
or at least a whole new set of questions to ponder.
Well, until we reach those boundaries, I'll be sure to keep my thinking cap firmly in place.
As will I.
Thanks for joining us on this incredible deep dive. Until next time, keep exploring, keep questioning, and never stop seeking out those aha moments.
Indeed. Curiosity, after all, is the driving force of discovery.
All right, getting right into it. This research paper, Killing Superalgebras in 2 Dimensions. Woo! I gotta say, it's a tough one, but super interesting,
Yeah, it's definitely a deep dive. But that's what we're here for, right? To unpack these complex ideas.
Exactly. And this paper, it really takes us down the rabbit hole. We're talking about supersymmetry, hidden dimensions, the works.
Some pretty mind-bending stuff. But at its core, supersymmetry is this idea that every particle we know of has a secret twin. We call it a superpartner.
Like a mirror universe of particles or something. Have we actually seen any of these superpartners?
Not yet. Not directly, anyway. But the math behind supersymmetry is so elegant, so compelling, that physicists believe there's got to be something there.
So we're talking theoretical physics here, but high-level theoretical physics. And that's where these killing superalgebras come in, right?
Exactly. Think of them like blueprints.
Blueprints.
Yeah, blueprints. But for these supersymmetric spaces, they help us understand the hidden structures, the symmetries within these theoretical spaces.
Okay, I'm trying to wrap my head around this. It's like we're trying to map out a universe we can't even see.
In a way, yes. And these killing superalgebras, they're the keys to understanding how everything works in this hidden world.
And this paper, it focuses on how these superalgebras play out in 2-dimensional spaces.
Right.
But why 2 dimensions? I mean, our world is 3-dimensional, right? At least.
It seems limited, I know. But working in 2 dimensions actually simplifies the math quite a bit.
Ah, so it's like a starting point.
Exactly. It allows us to develop the tools and insights we need to eventually tackle those higher dimensions.
Like a testing ground for these really complex ideas.
Precisely. Now, to analyze these superalgebras in 2D, the researchers use a tool called Spencer cohomology.
Okay, I'm going to be honest, that one sounds a little intimidating.
Chuckles. Yeah. It's a mouthful, I know. But it's really not as scary as it sounds. Imagine you have a shape, say a triangle.
Okay, a triangle.
Now picture stretching it, twisting it, maybe even morphing it into a square.
Okay, I'm with you.
Spencer cohomology helps us understand how much we can change a mathematical structure, like a killing superalgebra, without breaking it.
So it's like finding the breaking point of these mathematical structures.
In a way, yes. It helps us understand their limits, their flexibility. And in this paper, the researchers use it to explore killing superalgebras in two specific types of 2D spaces.
Okay, and those are?
Riemannian and Lorentzian.
Riemannian. I remember that from a previous deep dive. It's like the surface of a sphere, right? All curved.
Exactly. You got a great memory. Lorentzian spaces, on the other hand, they incorporate time as a dimension.
So more like the space-time of our universe.
Exactly.
Okay, this is where I start to get a little lost. We've got these spaces, these superalgebras. But how do we actually picture them, work with them? It all feels very abstract.
Well, that's where things get really interesting. One way we can start to get a grip on these superalgebras is through something called squaring maps.
Squaring maps, yeah, those have something to do with spinors, right?
We got it. Spinors are like, Imagine tiny arrows pointing in a specific direction. They describe a fundamental property of particles, their spin.
Spin, like a particle's rotation.
Sort of. But it's a bit more complicated than that. It's an intrinsic angular momentum. Think of it like a particle always has this spin arrow attached to it, pointing somewhere.
Okay, and these squaring maps, what do they do with these spin arrows?
Well, a squaring map takes two of these spinors, two arrows, and combines them in a way that gives you a vector.
And a vector, that's like an arrow with more information, right?
Yeah.
It has both direction and magnitude.
Exactly. It tells you not just which way something is pointing, but also how much oomph it has in that direction.
Okay, I'm following so far.
And here's where it gets really cool. Depending on the kind of space we're in, Riemannian or Lorentzian, these vectors can have different causal property.
Causal properties, meaning like related to cause and effect.
Exactly. You see, in a Lorentzian space, like the one we use to describe our universe, we have to take into account the speed of light.
Right, because nothing can travel faster than light.
Precisely. And that's where this thing called the Fiers identity comes into play.
The Fiers identity.
It's a mathematical tool that helps us determine if the vectors we get from our squaring map represent movement slower than, at, or faster than the speed of light.
So it's like a speed limit for these theoretical particles.
In a way, yes. It tells us which movements are physically possible within these different types of spaces.
Okay, that makes sense. But how does this Fiers identity actually work? It sounds incredibly complex.
It is pretty high-level math, but at its core, it's a tool for simplifying expressions. It lets us take these really complicated equations with spinors and make them, well, manageable.
So we can actually make sense of them.
Exactly. And when we simplify these equations, we uncover hidden relationships, patterns that weren't visible before.
Okay, so we've got squaring maps, these vectors, the Fiers identity. It feels like we're building a toolkit to explore this hidden supersymmetric world. But there's one more term I keep bumping into. Killing spinors. What are those exactly?
Yes. Killing spinors. They're key to understanding how all of this abstract math connects to the actual structure of these theoretical spaces.
Okay, so they bridge the gap between the math and the actual shape of these spaces.
You could say that. In simple terms, killing spinors are these special types of spinor fields that are, in a way, parallel within these spaces.
Parallel, but how can a spinor field be parallel? It's like saying a magnetic field is parallel. It doesn't quite compute in my brain.
Think of it this way. Imagine you draw a straight line on a flat sheet of paper.
Okay, got it.
Now roll that paper into a cylinder. The line is still straight from its own perspective, even though it now follows the curve of the cylinder. Right?
Yeah, I see that.
Killing spinors are like those straight lines, but existing within these curved, higher dimensional spaces.
So they kind of tell us how these spaces are curved.
Exactly. And depending on the types of killing spinors present in a space, they actually give rise to specific geometric structures.
Wait, hold on. You're saying these killing spinors can dictate whether a space is shaped like a sphere, a saddle, or something else entirely.
That's the amazing part. It's like they're embedded with information about the very fabric of the space itself.
That's incredible. We've gone from these abstract superalgebras to like actually visualizing the potential shapes of different universes, but we're still just working with two dimensions, right? what happens when we try to apply all of this to our own much more complex universe? That's the big question, right? How do we go from these simplified models to understanding something as complex as our own universe?
It's a challenge, for sure. But that's what makes this research so exciting. It's like we're building up a whole new set of tools.
Tools to explore the universe on a whole new level.
Exactly. And the things we're discovering in these lower dimensions, these connections between killing spinors and space-time geometry, they give us clues.
Clues about how our own universe might be structured.
It's a possibility. It suggests that there might be this deep underlying mathematical framework that governs everything.
Okay, now that's a mind-blowing thought. But this paper, we've said it before, it's really just a starting point.
Oh, absolutely. We're just scratching the surface here.
So where do we go from here? What are the next steps in this research?
Well, the authors mention a few possibilities. Exploring these ideas in higher dimensions, for one.
Moving beyond these two-dimensional models.
Exactly. And also looking at different types of spaces with different signatures.
Even more abstract than the ones we've talked about already.
It's all about pushing the boundaries, seeing how far we can take these ideas. Who knows what we might find?
It's like we're setting out on an expedition into uncharted territory.
And with these new mathematical tools, we have the potential to make some incredible discoveries.
This has been an amazing journey. We've covered so much ground, from abstract algebra to the potential shape of the universe itself. It's incredible how much is still out there just waiting to be discovered.
It really is awe-inspiring.
And for anyone listening, remember, curiosity is key. Keep asking questions, keep exploring.
You never know what you might find.
That's a great place to wrap up. Thanks for joining us on this deep dive. Until next time. Okay, we're really getting into it today. Diving into some seriously complex stuff. We've got this paper, Killing Superalgebras in Two Dimensions. And wow, that title alone, right?
Yeah, it's a mouthful. But honestly, the idea at the heart of it is pretty cool. Basically, imagine using like pure math to try and understand the universe's fundamental symmetries. That's kind of what this paper is getting at.
So we're talking about some pretty high-level theoretical physics here, right?
Absolutely, yeah. But what makes this paper really interesting is that it takes these superalgebras and looks at them in a simplified way, in just two dimensions.
So it's like they're creating a smaller, more manageable model to work with.
Exactly. Like, you know those insanely detailed model ships? They might not sail, but they help us understand how the real deal works. This is kind of like that.
Makes sense. But even with a simplified model, I'm already running into terms I don't quite get. Like killing spinors, what even is that? And don't even get me started on Spencer cohomology. It sounds like something out of Star Trek.
Yeah, they definitely sound like they belong in a sci-fi movie. But honestly, these terms are just fancy ways of describing some pretty neat mathematical concepts.
Okay, I'm listening. Demystify it for me.
Okay, so think of a killing spinor, like a special kind of mathematical object, right? And this object, it helps describe symmetries in specific spaces, especially those linked to something called supersymmetry.
Supersymmetry, like, is that what it sounds like?
Kind of. It's this idea in theoretical physics where basically all the particles we know about might have like partner particles we haven't found yet, sort of like a mirror universe of particles.
So for every electron, there's a theoretical selectron out there. Wild.
Exactly. Now, those admissible connections you mentioned, they're like the rules of the road for these killing spinors. They dictate how these spinors can move around within these spaces without losing their special symmetry properties.
So it's kind of the cosmic dance floor, but with very specific steps you have to follow.
That's a great way to put it. And then we get to Spencer cohomology, which honestly isn't as intimidating as it sounds. Think of it like a really, really detailed organizational system that mathematicians use.
An organizational system for killing superalgebras.
Exactly. It helps us sort them, understand their properties, kind of like imagine a library with millions of books, but no Dewey Decimal System, no card catalog, just utter chaos. Spencer cohomology is that missing system for these superalgebras.
Okay, so it's like bringing order to the chaos of the theoretical physics library.
Right. And within this organized system, there's this other key concept the paper digs into, Clifford algebras.
More complex terms. Hit me.
They're actually pretty elegant when you get down to it. Basically, they provide a way to represent geometric transformations like rotations or reflections, but using algebra.
So instead of trying to picture a rotation in your head, you can express it with an equation.
Exactly. And in this paper, Clifford algebras are super important because they help define those admissible connections and killing spinors we were talking about earlier. They're like the fundamental building blocks.
So it's like Clifford algebras provide the language we need to even talk about these other concepts.
Exactly. Now, building on that, another thing the paper brings up is the signature of a space.
Hold on, signature. Like signing my name on a dotted line. What does that even mean when we're talking about, well, whatever space these superalgebras exist in?
Uh-huh. Good question. It's not about autographs, that's for sure. In this context, a space's signature is all about its fundamental geometric properties. How do distances and angles behave within that space? The paper zeroes in on two main types, Riemannian and Lorentzian.
Okay, I'm lost again. What's the difference between those?
All right, so picture Riemannian geometry like the geometry of our everyday lives. You walk 3 steps forward, 2 steps back, you're 1 step from where you started, right? Pretty straightforward.
Right.
Lorentzian geometry, though, that's where things get kind of trippy. That deals with space-time, the fabric of the universe as Einstein described it.
Oh, so Riemannian is like our normal flat world, and Lorentzian is where things get all warped by gravity and time itself.
You got it. And here's the kicker. The paper finds that the kind of signature a space has directly affects what kind of killing superalgebras can actually exist there.
Wait, so you're saying depending on whether we're talking about a Riemannian space or a Lorentzian space, the types of killing superalgebras we might find there are different.
You got it. It's like the difference between baking a cake in a normal oven versus one with like its own gravitational pull, the environment makes a huge difference.
Wow, that's really interesting. But if the type of killing superalgebra depends on what kind of space it's in, how can we tell them apart? How do we even begin to classify them?
That, my friend, is where things get even more interesting. That's where we get into squaring maps. They're like these special mathematical functions that help us reveal the hidden relationships within these superalgebras.
Okay, so we've got these squaring maps acting like mathematical detectives, right? Uncovering the secrets of these killing superalgebras. But you mentioned another tool earlier, something about killing spinor equations. What are those all about?
Right. So remember how we talked about killing spinors being these like special objects that describe symmetries? Well, these equations, they're like the rule book these spinors have to follow if they want to exist within a specific space.
So it's like if a killing spinor wants to get into the club, let's say, a Riemannian space club, it's got to pass a test, and that test is based on these equations.
Exactly. And the really cool thing is that by actually solving these killing spinor equations for a given space, the researchers could figure out precisely which types of killing superalgebras could exist there.
So if I'm picturing this right, we can take a space, say a Riemannian space, plug that into these killing spinor equations, and boom, we get a list of all the possible killing superalgebras that can hang out there.
You got it. It's this amazing link between, like, abstract algebra and the actual geometry of these spaces. And it gets even cooler. Remember how we talked about Spencer cohomology being like a library catalog system for killing superalgebras?
Right, the Dewey Decimal System of abstract algebra.
Well, the paper takes that idea and runs with it. It uses Spencer cohomology to explore not just which killing superalgebras can exist in these spaces, but also how many different types you could have.
So it's not just about whether a killing superalgebra can exist, but also about how much variety we can find in that space. Like some spaces might be a jungle of different superalgebras, and others are like a desert with just a few hardy species.
That's a great analogy. And this whole idea of diversity leads to a really exciting area, the realm of maximally supersymmetric killing superalgebras.
Oh, there we go with supersymmetry again, those hypothetical partner particles we talked about earlier.
Exactly. Now, maximally supersymmetric theories, they suggest that there's like a maximum number of these superpartners, and these theories have some really neat mathematical properties.
So more superpartners, more symmetry.
Essentially, yes. And this increased symmetry in these maximally supersymmetric theories, it often makes the math a lot more elegant, a lot simpler, which physicists really like. There's this underlying idea that the universe, at its core, is probably pretty elegantly simple.
Okay, I'm following you. So how do these maximally supersymmetric theories tie back to the killing superalgebras?
Well, the paper looks at what happens when you focus on the killing superalgebras that specifically relate to these maximally supersymmetric theories. And what they find is that these specific types of superalgebras are really picky about where they decide to exist.
Picky how? Like they only want to be in spaces with ocean views. What are we talking about here?
Not exactly ocean views. But remember how the paper connects killing superalgebras to, like, Riemannian and Lorentzian spaces? It turns out these maximally supersymmetric ones, they can only exist in a super-limited number of spaces.
So they're like the rare orchids of the killing superalgebra world, only found in very specific, very special environments. What kind of spaces are we talking about here?
Well, one of the spaces that pops up is particularly interesting for physicists.
You were saying that one of the spaces where these maximally supersymmetric killing superalgebras like to hang out is especially interesting to physicists. What is this special space?
It's called anti-de Sitter space, or ADS for short, and it's a bit of a head-scratcher.
ADS space, right. I think I've heard of it, but remind me what makes it so special and why are physicists so into it?
Okay, so imagine a space, right? Yeah. But the farther you travel from any given point, the more space itself curves inward. It's like if you shine a beam of light in this space, it wouldn't go in a straight line, it'd curve back towards you.
Whoa, that's pretty wild. It's like the space itself is constantly folding in on itself. Why would physicists think something like that is elegant or simple?
It's all about the math. See, ADS space, as weird as it sounds, actually makes a lot of the equations physicists use way simpler, especially in string theory.
String theory, of course. I knew we couldn't have a conversation about the nature of reality without string theory popping up.
It's pretty hard to avoid when you're talking about, like, the most fundamental levels of the universe, you know?
Yeah.
Just a quick refresher for our listeners. String theory basically says that the universe isn't made of point-like particles, but rather these teeny tiny vibrating strings of energy.
Right.
And get this, some string theorists actually think that our entire universe might actually exist inside this higher dimensional ADS space, kind of like a sheet of paper floating in a room.
Okay, so let me see if I got this straight. We've got these maximally supersymmetric killing superalgebras, which are already pretty unique as it is, right? And these special superalgebras, they seem to really like being in very specific spaces, one of which is this bizarre inward curving ADS space. And now you're telling me that string theory, this theory that's trying to explain, well, everything, thinks our universe might just be hanging out inside this ADS space. I think I need a minute to process this.
And that's what's so amazing about this stuff, theoretical physics, mathematics. It takes us to these incredible places that really challenge how we think about reality.
Yeah.
This paper really shows us just how interconnected these fields are. It's like we're using abstract algebra to look for patterns in the fabric of the cosmos.
Yeah. I've got to say, this whole deep dive has been a wild ride. We started with these totally abstract killing superalgebras, then we explored how they're categorized, how they connect to the actual geometry of different spaces, and then we went even further, talking about supersymmetry, partner particles, even string theory, and ADS space. It's a lot to take in.
It really is. And the thing is, we've only just scratched the surface here. There's so much more to the research, so many more details and complexities we just don't have time to get into in a single deep dive.
That's true. But I think you've given us a lot to think about. Like, we've really explored the idea that these killing superalgebras might be more than just mathematical curiosities. They might be clues to some deeper structure within the universe. Maybe even a structure tied to the very nature of space and time.
Exactly. And the deeper we go into these abstract mathematical realms, who knows what other incredible secrets about the universe we might discover, right?
Absolutely. And on that note, we'll leave our listeners with one final thought to ponder. If these elegant mathematical structures really can be linked to the very fabric of reality, and that's what this research suggests, what other hidden connections might we find between the world of abstract math and the physical universe we observe around us? Perhaps the universe speaks its own language, a language of mathematics, and we're just starting to learn the grammar.
Until next time, keep exploring, keep asking questions, and keep diving deep.
Hey there! Ready to dive into something kind of wild? We're talking about killing superalgebras in 2 dimensions.
It's a mouthful, right?
It really is, but stick with us because this stuff is seriously cool once we unpack it. Luckily, we've got expert speaker here to help us make sense of it all.
Happy to be here. It's going to be a fun ride.
So the title alone might scare some people off, killing superalgebras. What are we even talking about here? What's the big idea?
Okay, imagine trying to understand the most fundamental laws of the universe, like the blueprints of reality itself, right?
Like the master plan for how everything works.
Exactly. We need a language to describe that, but instead of words, we use math. And that's where these killing superalgebras come in. They're like a mathematical code that helps us understand the structure of the universe, especially its symmetry.
Okay, I'm intrigued, but I gotta be honest, this is getting into some pretty abstract territory. How do we even begin to wrap our heads around it? Where do we start?
Well, the paper starts with some basic building blocks, like Clifford algebras. Think of them like mathematical toolboxes for understanding how things move and transform in space.
Okay, so like geometry on steroids.
Yeah, kinda. Imagine flipping a coin that's a reflection, a simple transformation in one dimension, right? Clifford algebras help us take that simple idea of a coin flip and generalize it to higher dimensions, even to spaces that are curved or twisted in ways we can't even picture.
So taking something we can visualize, like a coin flip, and then giving it a mathematical upgrade to explore more complex spaces.
Exactly. Now let's add another layer, spinors. We use arrows or vectors in physics all the time to represent things like velocity or force. Spinors are kind of like vectors' weirder cousins.
Weirder how?
Well, think about it. A vector tells you the direction and strength of something, like an arrow pointing. But spinors, they describe rotations.
So instead of the arrow itself, a spinor is like the twist.
That's a good way to put it. They're crucial for describing this fundamental property of particles we call spin. It's like each particle is doing its own tiny dance, and spinors help us understand the choreography.
Okay, I think I'm starting to see how these pieces fit together. We've got these mathematical tools for understanding transformations, these spinors that describe rotations. What's next?
Well, now comes the killing part in killing superalgebras. In physics, we're obsessed with symmetry, things that stay the same even when other things change.
Right, like the laws of physics should be the same whether you're here on Earth or like a billion light years away.
Exactly. Now imagine you're sliding a book across a table. It doesn't change shape or size, right?
Right, same book, just different spot on the table.
Exactly. We call that a rigid motion. Killing vectors are like the mathematical guardians of those rigid motions. They describe how something can move without getting squished or stretched.
So they make sure things keep their shape even when they're moving all around, like the cosmic equivalent of don't fold, spindle, or mutilate.
Yeah, kind of like that. And what this paper does is it connects these killing vectors to those spinors we were talking about earlier, all through these things called squaring maps.
Squaring maps. You're not making this easy on me.
All right. Think of squaring maps like translators between two different languages. They're the bridge between the world of rotations, those spinors, and the world of rigid motions, those killing vectors.
Okay, I can kind of see that. So different squaring maps would be like different ways of translating between these mathematical languages.
You got it. And the cool thing is, different choices of these squaring maps lead to different kinds of geometries, different kinds of spaces.
Okay, now you're speaking my language. Different geometries, like different shapes. But we're not talking about like squares and circles here, are we? We're talking about something way more complex, right?
Oh, absolutely. And what the researchers found is that some of these killing superalgebras, when you use the right squaring maps, they seem to perfectly describe the symmetries of some really weird spaces, like hyperbolic space.
Hyperbolic space. Okay, I've heard of that, but I definitely can't picture it.
Right, it's not easy. Picture a saddle shape, like something you'd see on a horse. That's a good starting point. What's wild about this kind of space is that it doesn't follow the same rules as the space we experience every day, like parallel lines. In hyperbolic space, they actually curve away from each other.
Wait, really? So the further those lines go, the further apart they get. That's wild.
It is. And here's the kicker. That weird, counterintuitive hyperbolic space, it actually pops up in Einstein's theory of general relativity.
Wait, so we're saying there might be a connection between this head-spinning math and the actual fabric of the universe?
You got it. This paper suggests that these killing superalgebras might be directly related to the structure of our universe.
Okay, my mind is officially blown. So we're saying that this paper is hinting at a connection between these abstract killing superalgebras and the way our universe is put together. But how do researchers actually explore that connection? What are they looking for specifically?
They're trying to figure out if certain types of these superalgebras only work in certain types of universes, like trying to find the right key for a specific lock.
A cosmic lock and key situation. Okay, I like that. So how do they go about finding these matches?
Well, they use a whole bunch of advanced math, but one tool they use is something called Spencer cohomology.
Spencer cohomology. All right, you're going to have to break that one down for me.
Imagine a giant library, right? But instead of books, it's filled with all the possible universes, each with its own unique shape and structure.
Okay, I'm picturing a cosmic library. Infinite rows of universes, each one stranger than the last.
Exactly. Spencer cohomology. It's like the cosmic Dewey Decimal System for that library. It helps us organize all those different universes, categorize them based on their properties.
So they're using this Spencer cohomology thing to sift through this vast cosmic library and see if they can find any patterns, any connections between the math of killing superalgebras and the types of universes they might describe.
You got it. And what they found is that some of those killing superalgebras we talked about, they seem to have a preference, so to speak, for certain types of geometries, like that hyperbolic space we talked about, but also things like anti-de Sitter and de Sitter spacetimes.
Okay, those names ring a bell, but I definitely need a refresher. What are those again?
Think about our universe, not as a flat sheet, but curved, bent by gravity. Anti-de Sitter space. Imagine a universe shaped like a hyperboloid, like a saddle but in 3 dimensions and stretching through time as well.
So a saddle-shaped universe. I'm trying to wrap my head around that visual.
It's wild, right? And gravity in this kind of universe, it pulls things together. Now, de Sitter space, that's the opposite. Picture a universe shaped like a sphere, always expanding, pushing things further apart.
So anti-de Sitter, things get pulled in, de Sitter, things are pushed outwards. Got it. But we were talking about killing superalgebras. How do these weird curved universes connect to all that?
That's the amazing part. These cosmological models, they emerge naturally from the math. The researchers were exploring those killing superalgebras and boom! Suddenly, these different universes start popping out of the equations like they're the natural consequence of the math itself.
So it's like the math is saying, hey, if you want a universe with these specific mathematical properties, these are the kinds of spaces you can have. It's like the math is dictating the possibilities for reality.
Exactly. And remember those squaring maps we talked about? The ones that connect spinors and killing vectors.
Yeah, the translators between those mathematical languages, right?
Right. Well, it turns out the choice of squaring map, it doesn't just determine the geometry. It also dictates the properties of something called, get this, killing spinors.
Hold on, killing spinors. Are those different from the regular kind? We're piling on the concepts here.
You're right to ask. We already talked about how regular spinors, they describe rotations, right? Well, killing spinors, think of them like the elite squad of spinors. They're like the Navy SEALs of the spinor world.
Okay, so tougher, stronger, faster spinors. I'm in. But what makes them so special?
They satisfy some very specific and very demanding mathematical equations. And these equations, they're not just some random mathematical quirk. They're often like little flashing neon signs pointing to something called supersymmetry.
Ah, supersymmetry. We hear that word thrown around a lot in physics. It's the idea that every particle has a secret twin, a supersymmetric partner.
Right, you got it. And finding evidence of supersymmetry would be huge. It would be like finding the missing piece of the puzzle when it comes to understanding how the universe works at its most fundamental level.
Okay, so supersymmetry is a big deal. But how do we get there from these killing spinors? I'm not seeing the connection yet.
Well, these killing spinors, they hold clues. By studying their properties, by analyzing those demanding equations they satisfy, researchers are hoping to find those clues that might lead us to evidence of supersymmetry in our universe.
So it's like these killing spinors are carrying around a map to supersymmetry, and we're trying to decode it.
You're getting it. Now, here's where the squaring maps come back into play. Depending on which squaring map they used, the researchers found they would end up with different types of killing spinors.
Different types? Like, what, are there spinor factions now? Are they fighting each other for dominance in the quantum realm?
Not quite. Think of it more like different dance styles. They found that some squaring maps lead to what they call geometric killing spinors, while others resulted in skew killing spinors.
Geometric killing spinors, skew killing spinors. Okay, you're using big words again. What's the difference and why should I care?
Don't worry, it's not as complicated as it sounds. Remember how those killing vectors describe rigid motions? How things move without changing shape? Well, those geometric killing spinors, they're like the master architects of that movement. They're intimately connected to those rigid motions.
Okay, I'm with you. And what about the skew killing spinors? What's their deal?
Those guys are more about the twists and turns, the rotations and reflections themselves. If geometric killing spinors are the architects, these skew killing spinors are like the choreographers, focused on the dance of space-time itself.
Okay, I think I'm getting it. We've got these two different dance crews of killing spinors, each with their own specialty. But how does this all tie back to the universe itself? How does the type of squaring map and the type of killing spinor it produces actually influence the kind of universe that emerges from the math? Okay, I'm still trying to connect all the dots here. We've got our squaring maps, which lead to different types of killing spinors, the architects and the choreographers, as we're calling them. But how does that choice, way back there in the math, actually affect the kind of universe we end up with? It seems like a pretty big leap from those tiny spinors to, like, the entire cosmos.
It's a big leap, but the math holds it all together. Remember how we said that some killing superalgebras seem to prefer the weird hyperbolic space? Well, it turns out that connection only really works if you've got those geometric killing spinors in the mix, those master architects.
Ah, okay, so different type of killing spinor, different set of rules, different kind of universe.
Exactly.
Okay.
It's like the skew killing spinors, those choreographers, they just don't quite fit with that hyperbolic space. They're doing their own thing, exploring different geometric possibilities. But the researchers, they were really intrigued by that connection between geometric killing spinors and hyperbolic space, so they decided to dig even deeper. They started analyzing the specific equations that these geometric killing spinors have to follow, and that's where things got really interesting.
Okay, more equations. Just have to hold my hand through this part. What are these equations and what do they tell us?
These equations, they're called the killing spinor equations. Very creative, I know. But don't let the name fool you. They're like a powerful lens that lets us zoom in on the fine details of these spacetimes, these universes that the math is describing. They help us see the hidden connections between different aspects of these universes.
Hidden connections? Like what? Give me an example.
For example, they found this really elegant relationship between the curvature of space-time, think of that as how much it's bent or warped, and something called the killing function. And this killing function, it's all about how those spinors themselves actually change as you move them around in that space-time.
So it's like the shape of the universe itself is intertwined with the behavior of these tiny spinors. That's pretty mind-blowing when you think about it.
It really is. It's one of those moments where you see how deeply connected math and physics really are. And by studying these killing spinor equations, the researchers were able to uncover a whole bunch of these hidden relationships, these elegant connections that we never even knew existed before.
So what's the takeaway here? Why does all this matter?
It matters because it gives us new tools, new ways of thinking about some of the biggest mysteries in physics, like supersymmetry. Remember, we're still searching for evidence that this idea, this concept of every particle having a supersymmetric partner is actually true. And these killing spinors, those equations, those connections to hyperbolic space and other weird geometries, they're giving us clues, new avenues to explore as we continue that search.
I think I need a minute to process all of that. We started with coin flips and somehow ended up contemplating the fundamental structure of the universe.
Only in theoretical physics, right?
That's for sure. But seriously, this has been an incredible deep dive. Thanks so much for being our guide through this mind-bending world of killing superalgebras, spinors, and the search for cosmic symmetry.
It's been my pleasure. Always happy to geek out about some cutting-edge physics.
And for our listeners, if you're still with us after that wild ride, we salute you. If you want to learn even more about killing superalgebras, we've got links to the paper itself, some helpful background resources, and even some cool visualizations of hyperbolic space over on our website. So go check those out, keep those brains buzzing, and we'll catch you on the next deep dive.
Welcome to another deep dive. Today we're putting on our theoretical physics hats, so to speak. We're going to be diving into this September 2024 paper. The title's a bit of a mouthful, Killing Superalgebras in Two Dimensions.
Yeah, it's a mouthful for sure. But, you know, we're not going to go full-on physics lecture on you. No worries. Hopefully by the end, even if you haven't opened a physics textbook in a while, you'll be left with a couple of those aha moments.
I like those. Okay, so tell me more about this paper. Why this one for our deep dive?
So this paper, it really dives deep into this fascinating area of theoretical physics, really looking at, like, the hidden symmetries of the universe.
Okay.
But get this. They do it using a simplified two-dimensional model.
Hold on. A two-dimensional universe? Like, are we picturing a universe that's just flat, like a sheet of paper here? I mean, our universe is definitely not flat last time I checked.
No, you're right. It's definitely not. But that's kind of what makes this so interesting, right? When we study physics in this sort of flatland, it can actually, like, reveal some surprising things about our own universe, you know, even with all its extra dimensions and all the complexities and everything.
Okay, you've piqued my interest. But before we get lost in flatland, I think we need to back up a bit.
Sure.
The title mentions killing superalgebras, and I'm going to need a little help unpacking that one.
Okay, yeah. Let's start with symmetry then. It's a word we hear a lot in physics. Think about a snowflake, how it has those beautiful, repeating patterns. That's symmetry in action, right? And in physics, it's basically about properties that stay the same, even if you shift your perspective or you move things around.
Okay, keeping up so far. So how do we get from snowflakes to superalgebras?
So mathematicians, they have a way to describe those symmetries. They use something called Lie algebras, and these algebras really help us understand the structure behind those unchanging properties. But then it gets even more interesting when you add in the super part.
Ah, here come the superpowers.
Yeah, exactly. Superalgebras, they take those regular symmetries and they bring in this really mind-bending concept, supersymmetry. And this theory, it suggests that every single particle in the universe, it actually has a hidden superpartner.
Wait, so there could be a whole other set of particles out there that we just haven't found yet. That's pretty wild.
Yeah, it's a really cool theory. Huge implications, for physics, for cosmology, the whole shebang. But for now, maybe let's stick with our 2D universe for a sec.
Right. Back to Flatland. So, okay, we've got this flat universe. We're trying to understand its symmetries, maybe with a little sprinkle of supersymmetry on top. And this is where these killing superalgebras come in.
Exactly. You can think of them like the guardians of symmetry in this 2D world. Basically, they're these special types of superalgebras that are connected to the symmetries of space-time itself. So, how things move, rotate, translate, but all within this, simplified two-dimensional context.
So they're kind of like the traffic cops of this flat universe, making sure everyone's following the rules of the road.
Yeah, that's a great way to put it. And those rules, we call those connections, and they dictate how things move and interact in this 2D space.
Okay, got it. But hold on. We're talking about movement in a two-dimensional world. How does that even work? This paper mentions things like spinors and squaring maps. It's like we've walked into some physics funhouse.
I know. It's a lot of interesting terms, right? So think of spinors not so much as particles themselves, but more like the gears behind rotation in this 2D world. They sort of dictate how particles move and interact.
Okay.
And squaring maps are kind of like the instructions or recipes for how you combine these spinors to create movement in this flat space.
So it's not as simple as just going up, down, left, right in this flat land.
Exactly. There are all these different ways you can combine these spinors, and each combination will lead to a different kind of motion. Imagine a cosmic cookbook with all these recipes for moving through this 2D universe.
So we've got our ingredients, the spinors, we've got our recipes, the squaring maps. What do we get when we follow these recipes?
Well, each recipe, each squaring map, it kind of tells us something about the underlying geometry of the space. They lead to different bilinear forms. You can think of these forms as ways of measuring how similar or different two spinors are. Are they two peas in a pod, or are they complete opposites,
Interesting. So by studying these combinations, these relationships, we can learn something fundamental about the structure of this simplified 2D universe.
Exactly. And this paper, it uses this mathematical tool called Spencer cohomology. It's a way to analyze how these killing superalgebras, our symmetry guardians, change when we deform our 2D space.
Deform. Are we messing with the fabric of our flatland now?
Yeah, exactly. Imagine taking that sheet of paper we were talking about and twisting it, stretching it, bending it. We're looking at how these changes affect the rules of the game.
Okay, I think I'm with you, but why go through all this? Why study this pretend 2D universe? How does any of this connect back to our actual universe? The one with all the bumps and curves and, well, more than 2 dimensions.
See, that's the beauty of theoretical physics, right? These 2D models, even though they seem simple, they're like these testing grounds for much bigger ideas. And think of it this way. It's like building a miniature model of a skyscraper. You test out the design principles, see how things work, on a smaller scale before you go build the real deal.
So what bigger ideas are we testing out with our flatland model? What's the skyscraper, so to speak?
So in this case, it's supergravity.
Okay.
It's this theory that tries to unite Einstein's theory of general relativity, which explains gravity, right, and quantum mechanics, which is all about the really, really small stuff, particles at the subatomic level.
Right, trying to find that missing link between the really big and the really small, which has been a bit of a head scratcher for physicists for a while now.
Yeah, exactly. And this paper, it explores different types of 2D spaces with specific properties, like hyperbolic space, de Sitter space, and these spaces, they actually have counterparts in the models we use for our own universe.
So by messing around with these mathematical spaces in our simplified model, researchers can get insights into how supergravity might actually work in the real world.
You got it. It's a way to wrap their heads around these super complex ideas in a setting that's, a little more manageable. And get this. This is where it gets really cool. Supergravity, it's actually considered a possible path towards a theory of everything.
Okay, now we're talking about the holy grail of physics. But for those of us who need a refresher, what exactly is a theory of everything, and why is supergravity a good candidate?
So a theory of everything, it's like the ultimate goal in physics, right? It's a single framework that can explain all the fundamental forces of nature. Gravity, electromagnetism, the strong and weak nuclear forces, all in one go. It's like finding this master key that unlocks all the secrets of the universe. And supergravity, it's a really strong contender because it combines the force of gravity with the world of those teeny tiny quantum particles in a really elegant way.
So by studying these killing superalgebras and how they do their thing in these different 2D spaces, physicists are hoping to crack the code, unlock some of those universe's deepest secrets.
Exactly. And this paper, it takes a step further. It dives into this really intriguing area, imaginary killing spinors.
Whoa, hold on, imaginary spinors. Now we're going down a rabbit hole. What in the world does that even mean?
Yeah, it's a little much to unpack here, but just know that they're basically different versions of those mathematical objects we talked about earlier. You know, the ones that give us a handle on rotations, movements, all that, but in our flatland.
So like spinors, but from another dimension, a bit more abstract.
That's a good way to think about it. And, you know, because they're less explored than their real counterparts, there's this chance that they could reveal some really wild, unexpected connections between supersymmetry and, the very structure of our universe.
It's like taking that road, less traveled, but in physics, and you might stumble upon a whole hidden treasure trove of knowledge.
Exactly. That's what makes this research so exciting.
So we've gone from a simple sheet of paper to, a cosmic treasure map, right? Hunting for the universe's hidden code. It's amazing to think that these imaginary killing spinors, these less traveled paths, could be so important.
Yeah, it really shows you how much we still don't know, you know? We think about physics and it seems so concrete, so established. But then you get into these abstract, theoretical areas, and there's just so much more to explore.
It's like those old maps, right? With the "Here be dragons" written on the edges. We're really venturing into uncharted territory. But what's really cool about this paper is that it's not just about the math, even though that's pretty mind-bending on its own. It's about potentially changing how we understand the universe, at a fundamental level.
Oh, yeah, absolutely. This paper, it's basically saying to physicists, hey, pay attention to these imaginary killing spinors. They could be this key to unlocking all these new connections, right, between supersymmetry and, the very fabric of reality.
So what happens next? What are the potential implications here? Where do physicists go from here?
Well, one thing is to keep developing those mathematical tools, those frameworks, to really dig into these imaginary killing spinors.
Yeah.
Think of it like crafting these new lenses so we can observe the universe from a totally different perspective.
And what might we see with these new lenses?
Well, that's the million-dollar question, isn't it?
Yeah.
I mean, it's possible that by going down these less traveled paths, we could find solutions to some of those big, persistent problems in physics, like maybe even that unification of gravity and quantum mechanics, who knows?
Right.
Or we might uncover even bigger mysteries, things about the universe we haven't even thought to ask yet.
It's exciting and a little bit humbling, isn't it? This vast universe with all its secrets, these hidden symmetries, this underlying mathematical language.
It really is. And that's the beauty of physics, this constant journey of exploration, always discovering something new.
Well, on that note, I think we'll wrap up our deep dive here. We've gone into the world of killing superalgebras, explored the mysteries of imaginary spinors, all that good stuff. Hopefully you've come away with a little more appreciation for the power of theoretical physics, how it can potentially unlock these incredible secrets of the universe.
Yeah, and who knows, maybe someone listening will be inspired to, explore those uncharted territories themselves, see what wonders they can find.
Exactly. Keep asking those big questions and never stop exploring the world around you. Until next time.